Principal component analysis, or PCA, is a statistical method used to simplify complex data. In interest rate markets, we observe many different rates, such as 1-year, 2-year, 5-year, and 10-year rates. These rates usually move together because they are part of the same yield curve. Analyzing each of these rates individually can become complicated. PCA solves this problem by converting many correlated interest rates into a small number of independent components. In simple terms, PCA identifies the main patterns that drive movements in the entire yield curve. Instead of studying many rates separately, we can focus on a few major factors that explain most of the changes. This makes it much easier to analyze interest rate risk and understand how the yield curve behaves. Traditional regression analysis usually studies the relationship between a small number of variables. For example, we might try to explain the change in one interest rate using the change in another interest rate. The regression formula shown here represents this type of relationship between two variables. In simple terms, it measures how sensitive one rate is to the movement of another. However, regression becomes difficult when we have many interest rates, because we would need to analyze multiple relationships between each pair of rates. PCA takes a different approach. Instead of analyzing pairwise relationships, it studies all interest rates together and extracts a few common factors that explain their movements. Suppose we observe changes in several interest rates, such as 1-year, 2-year, 3-year, 4-year, and 5-year rates. PCA combines these rate changes using weighted coefficients to create new variables called principal components. The formulas shown here represent how each principal component is constructed as a weighted combination of different interest rate changes. Each principal component captures a particular pattern of yield curve movement. In practice, the first component usually represents a parallel shift, where all rates move up or down together. The second component often represents steepening or flattening of the yield curve, while the third component captures changes in curvature. Principal components have several important statistical properties. First, the total variance of all principal components is equal to the total variance of the original interest rates. This means PCA does not lose information. It simply reorganizes it into different factors. Second, the principal components are uncorrelated with each other. This means movements in one component do not affect the others, making risk analysis easier. Third, the components are ordered by importance. The first component captures the largest amount of variation in interest rates, the second captures the next largest, and so on. Because of this property, the first few principal components explain most of the movements in the yield curve. One of the most useful applications of PCA is in constructing hedging portfolios. Instead of hedging against each individual interest rate, we hedge against the main principal components that drive rate movements. The formula shown here represents how changes in interest rates can be expressed as a combination of a few principal components. A portfolio's exposure can then be measured with respect to these components. By taking opposite positions in hedging instruments such as bonds or swaps, we can neutralize these exposures. As a result, even though the market contains many different interest rates, we only need to manage a few key risk factors, making hedging much simpler and more effective.